Hi, my name is Carl Sterling. I'm going to explain simple harmonic motion and how to analyze it. This is from Chapter 4, Lesson 8. Alright, here we go. We are here on the Trig class page, and I've clicked on the My Math Lab and Pearson eText link here. I'm not doing the assignments like we normally would. If I click here on the chapter contents, chapter 4, and I come down to 4.8, and I click on the multimedia text, this will open up the electronic textbook for us. And it opens up to page 601. If we jump ahead to page 605, we can see the very beginning information about simple harmonic motion and how to model it, or how to graph it. A fellow classmate has already done their presentation on that. That was topic 18. They're showing the motion of a spring over time, a ball and spring. Now, whether this is multiple springs lined up or just a single spring that they're showing over time, if they are graphing it, it is just a single spring being shown over time. I guess if you had a V12 engine and it was an inline V12 engine, this could all be happening at the same time in that one engine. But in general, if it's showing the line, it's showing the line of a single ball and spring. It's not moving on a conveyor belt, it's just moving up and down from a single location. And it's showing it repeatedly over time at its different positions. They have the amplitude of the ball and spring. This ball and spring can travel up 4, or it can travel down 4. I will assume that's centimeters, but I'm not sure. They call that the amplitude here. When we go to analyze simple harmonic motion, we're going to call that the maximum displacement. So it can come up 4, it can go down 4. This is a cosine curve because it starts either at the top or bottom. Since it's starting at the bottom, that is a negative cosine curve. If I want to look at a single cycle, it's the amount of time it takes it to travel from one point and to return to that one point. So here a single cycle, or a period, is 6. And I can guess that that is 6 seconds. Or I could try to read, it might explain it somewhere. So my period here is 6 seconds. And that means that my frequency is going to be 1/6. So if this was second 0, second 1, second 2, second 3, second 4, second 5, second 6, it takes it 6 seconds to go through a cycle. And each phase is 1/6 of 6 seconds, or 1 second. So 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and 6 seconds. We call that the frequency. We call the time for one cycle the period. And we call the distance from 0 to the max, or from 0 to the min, the maximum displacement. Alright, we have jumped ahead to page 607, and as you can see, we now have analyzing simple harmonic motion. We have our value here. This was known as the amplitude, and now it's going to be known as the maximum displacement. We have the two other sections, the frequency and the time required for one cycle. This is also known as the period. And we have a couple formulas for those that I'd like to show you. We can see them on the following page. We do have pi over 6, the part that comes in between the sine or cosine. And simple harmonic motion can only be shown in sine or cosine. And the time, symbolized by the letter t. This part that's in between is known as omega. You know, alpha and omega, that's the beginning and the end. This is symbolizing the end of a cycle. We have pi over 6, and we need to ratio that up with our 2 pi, which is the standard cycle for a sine or cosine graph. Let's check out what the book had to say on that one. For finding the frequency, they do omega over 2 pi. To find the period, they do 2 pi over omega. So those are the only two differences. You really only have to find one or the other, and once you find one, the other is simply the reciprocal. Pretty simple. You only have to do the math for one, not for both. Let's try one together. An object moves in simple harmonic motion, described by distance equals 12 times cosine of pi divided by 4 time. Pi divided by 4 is our omega, and 12 is both the amplitude and the maximum displacement. 12. All right, our sample problem was written as d equals 12 cosine pi over 4t. And of course we know that that first number before cosine or sine is the amplitude. And we also know that that is the maximum displacement. That would have been the absolute value. If it were a negative, it would have become positive at that point. The only other things we have to worry about are the frequency and the period, and I can choose to do either one. My frequency is going to equal omega divided by 2 pi, or my period is going to equal 2 pi divided by omega. I can choose to do it either way, or I could choose to do it both ways. My omega is right up here. It is the pi over 4. So I can write this as pi over 4. Instead of being divided by 2 pi, I'm going to do times 1 over 2 pi. The pi's will cancel out. I'll be left with 1 over 8. If I have 1 over 8 here, I know I'm going to have 8 over 1 on the bottom. Instead of being times pi over 4, or pardon me, instead of being divided by pi over 4, this will be times 4 over pi. Pi's cancel out. 2 times 4 is 8. 1 times 1 is 1. So the frequency here is 1/8 of a cycle, or 1/8 of the total cycle per second. And 8 here is 8 seconds for one full cycle, per cycle, and up here was per second. We have jumped ahead to page 609 here, and this just so happens to be the next page, but this is the end of chapter 4. And this is a great place to find some sample problems. If you were like me, you're reading through the book and you're like, hey, why do they just give one sample problem and they don't even tell you the right answer? Well, you have to go to the end of the chapter or the end of the lesson to find those extra questions. So I have here some questions pertaining to analyzing simple harmonic motion, maximum displacement, frequency, and period. They haven't changed. By clicking on this icon, it will let us try some examples together. You can certainly try this yourself. I'll just go through a couple with you here. I'll try exercise 27, since I'm assuming that's the most complex, the later example. All right, this first one up, we have -2 sine 2 pi over 7. I know this is a sine graph, and it's going to start going downwards because of the -2. Displacement is the absolute value of -2. In this case, it is 2, and they even filled in the inches for me of 2. That was very kind of them. The frequency, I'm gonna do my period. I don't really care what they want me to do first, and I'll just work with the reciprocal after that. I know that my period is 2 pi divided by this, so it's going to be 2 pi times 7 over 2 pi. The 2 pi's cancel out, and my cycle is going to take 7 seconds. If my cycle will take 7 seconds, then if the entire frequency will take 7 seconds, then it will be 1/7 of a cycle for each second, and I just automatically know my final value of 7. All right, let's try that example. D equals -2 sine 2 pi over 7 t. A little hint here, whenever I see the 2 pi, I just instantly know the period is 7 and the cycle, or the frequency, pardon me, is 1/7. But we'll show the math here. We start off with our amplitude, or our maximum displacement. It is the absolute value of 2. So the amplitude, or the maximum displacement in this case, is 2. To figure out our period, we're going to use the formula 2 pi over omega. Oh, another way of writing that would be 2 pi over 1 divided by omega, which is 2 pi over 7. Of course, we rewrite that as 2 pi over 1 times 7 over 2 pi. We could have done 2 pi divided by 2 pi is 1. 1 divided by 7 is 1/7, and we would have done 1 divided by 1/7. But we can just cross cancel here and get 7 over 1. The period is 7 seconds per 1 cycle, and the frequency is going to be 1/7 of a cycle per 1 second. We can try another by clicking on similar question near the bottom. This one has a value of -6 before the sign. That's an absolute value, so it is 6 inches as the displacement. The frequency, well, 2 pi up top again, so I know I'm going to have the 2 pi down below. That means it's 5 seconds for the full cycle, and 1/5 of a cycle per second. And we can automatically fill in the 5 down below. You can have a little fun here at the end. We'll try to graph this situation. The formula for the harmonic motion in our last example was D equals -6 sine 2 pi over 5 time. Sometimes they like to put brackets on here. According to PEMDAS, you don't actually need those brackets. Now, if we wanted to put this into a graph to understand it better, sine or cosine graph, we can start with the positive values. And we're going to have our displacement going all the way down to -6, hitting 0 in the middle, and coming all the way up to +6. Since this is a sine graph, we know that it will start on 0, and there's been no movement to the left or right. We have already done our math to figure out that this will take a total of 5 seconds. So in the end down here I have my 5 seconds. And I want to split this into quarters. The quarters in this example are going to be 2.5 seconds, 3.75 seconds, and 1.25 seconds, because 5 divided by 4 is 1.25. I want to graph this. It is a -6, so it's going to start with that downward trend. We can bring it down to the -6 at 1 1/4, back up to 0 at 2 1/2, up to +6 at 3.75, and then back down to 0. If we wanted to graph this, it would look something like this, and of course it would continue on and might even continue on into the negative zone. So we've gone through one full cycle, and at each point here, I mean, if we really wanted to show the frequency, we could show that at each single second, although it wouldn't make much sense to show it there.